This video onwards, we shall work our way towards defining specific measures. In particular, we shall start with Lebesgue measure, which is basically what we call a length. We have already said that length is a measure, but how do I exactly define it? Now, of course, we start by saying that it has to be a measure and it must satisfy the obvious condition, namely if it is the number a and this is b, then the measure for this should be b minus a. Starting from this, we want to arrive at a measure defined over a suitable sigma algebra. And that suitable sigma algebra will be the Borel sigma algebra, which is generated by all open intervals. Now we want to do it rigorously. First, let us understand what is the task that we are undertaking. Suppose I ask you, what is the length of this subset? 1 and 10 to 12. This union. Now, I know that for intervals it is the length, but now this is not an interval. This is union of two intervals. Then what should the length be? Well, I know that it's a measure. It's supposed to be a measure. So, the length of this should be the length of this plus length of this, because there is no overlap. So, it should be 1 plus 2 equal to 3. Okay, what is the length of just a singleton? You guess that this is same as the closed interval 5 to 5. So, this length is also equal to 0. What should be the length of the rational numbers? Well, it is made up of countably many singletons. Each of them has length 0 because the measure has to be countably additive. So, this must have measure equal to 0. What should the measure be of irrationals? I know that for R, which is an interval, the measure is infinite. So this plus that should give me infinite. So this must be infinite. Now in this way, I can see that though I started with just intervals, I can manufacture more things out of it. But things might become complicated, like I might say what happens about the measure of the Cantor set. A priori, this is not entirely obvious. What should the measure be of Cantor set? And there is always the chance that maybe it is one of those bad sets for which I cannot define measure. So that is what we are now trying to head for, so that we have a clear definition of measure for every set in the Borel sigma algebra. The way we want to proceed should be in a sense general, so that we can use it for other measures as well. So we define a semi-algebra which is something much weaker than a sigma algebra. So I call it script D. It's a collection of subsets over some set S, that is collection of subsets of S. The first condition is the full set must be in script D, much like sigma field. It must be closed under finite intersection. If two sets are in this set, its intersection is also there. So by induction holds for any finite intersection. Now, this is something like saying it is closed under complementation, but not quite. If you take any set, its complement need not be in script D, but it can be expressed as the disjoint union of finitely many elements of script D. We are basically mimicking whatever we can say about intervals. Suppose I take the entire R and I take this interval from minus infinity to 0. And I take its complement, then that will be closed 0 to plus infinity. So its complement is again an interval, and so it lies in our set. But now suppose the interval that I take is like 0 to 1. its complement is minus infinity to 0 and 1 to infinity. So it is union of two things, disjoint union of two elements of script t. Now in case of interval, the complement is either made up of one single interval or made up of just two. But as I said, we are trying to proceed in a way that can be generalized to other things also. That is why we define semi-algebra in this way. So the running example that you should keep in mind are just all intervals in R. So while we are developing the theory in general, we are always keeping in mind the length example. So we have this result. Length is indeed a measure on the semi-algebra of all intervals. Now let's understand this clearly. I said only semi-algebra, so we are not into sigma algebra yet. By this I mean that suppose I have this semi-algebra of all intervals. I say that first of all, length of the empty set, which is also an interval in a trivial sense, that is 0. No problem with that. And the second thing is, if you give me any intervals, countably many possibly, or finitely many, these are all in script t and they are all disjoint, then naturally I want to say that length of their union should be sum of the length, but the problem is so far I have length defined only on the semi-algebra. Now I have length defined only on this interval. So how do I make sense out of this? Because I know if I take disjoint unions of some intervals, that need not be an interval. But my point is, if AIs are such that they are disjoint and I put this additional condition, this is in script. If someone gives me this, then indeed I have sum of lengths of AIs. So I had to put this as a separate condition. Later, when we shall finally finish the proof with sigma algebra, we will say if this holds, if this is sigma algebra, this must be there. But so far, I am just starting with intervals. So I have to put this condition. If you give me certain disjoint interval such that their union is again a single interval, then this is definitely true. A very humble statement, but that's all that I can make at this point. In the next video, we shall start building it up from semi-algebra to algebra to sigma algebra. So stay tuned for that.